focus the person. All right. So our main focus today is going to be on circular motion. Particularly circular motion focuses on objects moving in a circular path, just like we can see. Okay. So we can talk about the rotation, we can talk about the evolution. We are all referring to one thing of something moving around in a circular path. It will be moving towards one point. All right. So I want you to understand that whenever something is moving in a circle, there should be something that is making it to be put towards the circle, right? Because let's say if you have a ball, let's say this is where your hand is, then you've this is a rope connecting maybe, for instance, a ball. Then this ball is moving around. You're rotating it. Don't mind the drawing. We are so good at not drawing. Okay. So you see what's your hand? You're rotating this ball, right? So there is a force that is acting along the rope that is avoiding the ball like to move away from the ball, move away from the circular path. Like it's like a force putting it towards the center. Okay. The ball is at this point, it will still be put towards the center and it will be made to move in this same circular path. Okay. So what are we trying to say? We're trying to say when we've got something moving in linear motion in a straight line, there is what we call force, right? A force is actually what causes motion in linear motion, right? Of course, we know a force can be a push, it can be a pull. All right, so that's what makes something to move. And whenever you apply a force, what do we expect? According to the formula that we know, we expect an acceleration to result, right? Okay. So this is what we're trying to talk about. Now, if we know that a force is what causes motion in linear motion, what then would we say about circular motion? So what we are trying to say, or the point that we're trying to raise here is, when something is moving along a circular path, we expect that there's a force that should be putting it towards the center, okay, so that it continues moving in what? In the circular path. So that force, what makes something orbiting, for instance, the moon orbit around the earth, that force that causes that, so that it doesn't like go away or move away from the circular path. That's what you're trying to call the centripetal force. So whenever you ask of the force that causes something to move in a circular path, it's a centripetal force. The centripetal force pulls the object moving in a circular path towards the center. All right, so the centripetal force is denoted by capital letter F with a subscript of small letter C. So centripetal force. This is the force that causes something to move in a circular path. Right. So we have got a lot of applications when you talk about circular motion. It's very important. It's a very important aspect of our day-to-day lives. Okay. Okay, let me go to the next page. All right. So if we talk about the roundabout, we know you've got cars coming maybe from this side. There's a road coming from the other side. Okay. So when you're moving in that way, that is a practical application of a circular motion. The tires will be moving in circular motion, then the car will be moving in a linear straight. Okay, so what are we trying to say? So we are trying to say that rotational motion has got a lot of practical applications in our day-to-day lives. If we talk about the satellite dish, for you to be watching your DSTV, whatever you're watching there, if you're using a satellite dish, it also uses the principle of circular motion there are over 600 satellites that have been put in space. Okay, they all use the principle of circular motion. They rotate around the Earth. So they are the ones that are able to get the information from the transmitter, from the station, then they will send it to the satellite dish. So all these things are using the principle of what? Circular motion. Okay, another example, a real life application is not even, let me say, in nature as well. We've got the moon rotating, rather orbiting around the Earth in a circular way. So that is a practical example of circular motion. So of course, I've said for us to have circular motion, there is need to have what? A centripetal force. So we've got different types of centripetal forces that causes things to move in a circular path. Okay. So some of the most important ones that we will talk about is tension. So the example what I gave, when maybe you've tied something to a cord or your rope, maybe a ball. So when you're rotating that, so what's causing the centripetal force in that case is the tension. Then the moon orbiting around the Earth, what causes the centripetal force in that case is gravity. Okay. Then the other type of centripetal force that we can talk about is friction. So when the car is moving around about, friction that is providing what? The centripetal force. Okay. So generally the centripetal force is given by this formula. We know, of course, in linear motion that our force is equivalent to what? To m by a. All right. So for in terms of the centripetal force, the formula that we are supposed to use is this one. V squared, mv squared divided by what? Divided by r. Okay. So this is the linear motion part. So if you look at this part, we'll notice that the mass is common. Okay. So implying that this part, v squared over r, represents what? The acceleration, which is the centripetal acceleration of so something moving around or orbiting is always has an acceleration that is given by the square of the velocity at a given point divided by the radius. So these are the introductory formulas that we should know as we talk about rotational motion. Okay, so I've talked about, I've given you some practical examples. Of course, I've not talked about the magnetic steps, all those things. When the CD, when you're playing a DVD, we expect that CD to be rotating inside the DVD player. All that is an application of what? Circular motion. So what are we trying to say? So we're trying to say for that to continue rotating in that path, there is a force that is putting it towards what? Towards the center. All right. Is there any question before I move on to different parts of this topic? All right, so assuming there are no questions, we'll move on to the next part. All right, so it's very important to take note of this information as well. Okay, so every circle has what we call radius, right? Every circle has what we call the radius. Very important. So from there, let's talk about the concepts that we are aware of. Okay, we'll be shifting from kinematics going to circular motion. All right, so under kinematics, when you talk about linear motion, we have what we call velocity. We all know what velocity is, right? The rate of change, yeah. So it's a rate at which something is changing in terms of distance. That's velocity. The rate of change of distance in respect to time. So velocity. So velocity under linear motion, we denote it by a letter V. That's our velocity. So now, when you got to, okay, so this is talking about translational motion, or we can call it linear motion. So let's have like something like a table. Okay. Then on the other side, let's have something under circular motion. Let's not other components to be part of circular motion. Okay. So under linear motion, we have velocity. Under circular motion, we have the counterparts to be, it's called the angular velocity. Okay. So we're just adding the angular velocity. So it's denoted by letter omega. Okay. She's like a W and something like that. Okay. So how do we do the conversions between the two? How do we convert from linear velocity to the angular velocity? So the linear velocity is equal to the radius divided by the angular velocity. So we're just multiplying the components in circular motion by the radius. It's supposed to be equivalent to what? To the linear velocity. Is there any question about the velocities between the two counterparts? Okay. So the other part that we know under linear motion, we have what we call the displacement. We call it the distance. It's the same, right? Also, you know, displacement is a distance with direction. Okay. So under the circular motion, we just call it angular displacement. Okay. Angular displacement. Then for our displacement, under linear, we just use the letter S. Others may use D. It's one and the same. Anyway. So, but for angular displacement, what do we use? We use the angle theta, right? What are we trying to say? So we're trying to say when something is moving along let me say a straight line, like that. So this is going to be the S or the distance. That's what we're trying to say, S or D, right? That's what we have there for the linear motion. Now, if you're talking about something moving in a circular path, what are we going to talk about? We're going to talk about it in terms of the angle that it has made. Let's say if it moved from this point, let me use a different calculator. So let's say if it moved from this point going to this point. So we're not going to talk about the arc made there. We're going to talk about the angle that it has made. Okay. So we are saying under circular motion, the displacement, the angular displacement is denoted by what? By theta. So yes, so that's what we're trying to say. Then just the same, if you want to convert the linear displacements to the angular displacement, the formula that connects the two is radius multiplied by what? By theta. Okay. Are we together? Are we together?
Yes, sir.
Okay. The last part, acceleration. So for acceleration, we have acceleration there. No, acceleration is just small letter, eh? So angular acceleration. So it's denoted by letter alpha, just like that. Oh, let's go it, yeah. So we expect this one to be related to that one by R, like that. That's what we have. Are there any questions? Any questions?
No question.
Okay. So I want us to go back to the equations for kinematics. Okay. So help me with the equations under kinematics. There are about 4. Help me with those equations. Hello.
V is equal to plus AT. Velocity is equal to initial velocity plus acceleration times time.
So V final, V initial plus acceleration by time.
Yes.
The other one, somebody else. Somebody else there, your friend has given us one.
The other one is displacement is equals to half open brackets initial velocity plus final velocity close brackets times time.
Come again.
Displacement is equals to half open brackets initial velocity
Is
plus
equal to
final velocity.
open brackets. Initial velocity.
Initial velocity plus final close times time.
Okay, interesting. I didn't know this one. Okay, the other one.
V final squared
Final squared
is equals to V initial squared plus 2 acceleration times displacement.
plus like this.
2 AF.
Okay, the other one. Okay, my guys. Hurry up.
Displacement is equal to initial velocity times time plus half acceleration times time squared.
Okay. All right. So my area of interest, I wanted to focus on this one, and this one. So I want to talk about the counterparts, their counterparts in terms of circular motion. So what did we say? We said velocity under circular motion is denoted by what? Hello?
Omega.
Okay. So this equation we expect it to come out this way. The acceleration supposed to be what?
Alpha.
Like that. For this one, So we're just substituting something that is equal to the displacement is what? What is the counterpart?
Theta.
Right. And the last one, what are we going to have? Hello?
The last one, sir.
Yes. What are we going to have?
Alpha, oh, theta, sorry, is equals to
Let me write this property. Theta is equal to, that is
yes,
our
omega
omega initial
initial
by time plus half
times alpha t squared.
So you're not required to know these equations. If you can, well and good. But if you know one side, you are well. Just know that this is represented by that. This is represented by that. That's all you get. Okay, I believe we are together. Any questions concerning the equations? Any questions? I believe everyone has understood. People are quiet. So I want us to go back to the concept of a centripetal force in terms of calculations. Okay. I'm trying to open the worksheet so that we can try to look at it. Okay. Okay. It's okay. Okay. Tough questions. What we need to tackle together. So Chichi inbox me after the meeting. Are you able to get me? Hello, Chichi, inbox me after the meeting.
All right, sir.
So we've done the introduction. You guys have missed. We talked about the introduction to the circular motion. Let me just try to show you what we've done already. So we talked about how to derive these equations. Okay. So we started talking about the centripetal forces. So we say the centripetal force is a force that allows us to convert, it makes something that is moving in a circular motion or orbiting to move towards the center. Without a centripetal force, nothing could move along what? A circular motion. So we say the centripetal forces, we can have different forms in terms of when you've tied something to a cord or a rope, we expect the tension that will be acting via the same cords to provide the centripetal force. In terms of talking about the moon orbiting around the Earth, we talk about gravity being the centripetal force. Then in terms of the cars moving around when we talk about tension, that is friction providing centripetal force. So now I want to look at some examples to see how we can apply that concept. Of course, we say that our centripetal force is supposed to be given by the mass multiplied by the velocity squared divided by the radius. Okay. So now let's try to look at the worksheet. All right. The question is a little tough. Okay. So we're just going to use the same concept. All right. So in 1994, Mata Jagdamba of India had very long hair. It was 4.23 meters long. Suppose Mata conducted experiments with her hair. First, she determined that one hair strand could support a mass of 25 what? 25 grams. So take note, we've been given the mass here. She then attached a smaller mass to the same hair strand and swung it in the horizontal plane. If the strand broke when the tangential speed of the mass reached 8.1 meters per second, how large was the mass? Okay, so a very interesting question. So we have to take note of the data that we've been given. Let me copy this question to the board.
Arriba. Baba brave funny but
So let me copy this question to this board so that we are able to see what we are talking about. Okay. Right, so let me just add the text. Are we able to see the question?
no.
You can't see?
I'm able to see now.
Okay, so this question we're trying to focus on the centripetal force. So let's look at the data that we've been given. So we've been given 4.23 meters. Okay. All right. So consider our head to be like the central part of the circle. All right. So what are we trying to take as an assumption? We're trying to take an assumption that the 4.23 meters is going to be our radius. Okay, what other information have we been given? We've been given the first mass, that was 25 grams. Okay. She then attached a smaller mass to the same hair strand and swung it in the horizontal plane. So it was like so this is our head. Then this is the same string. So the same strand of air. It had the radius of 4.23. So then the mass, first mass that was there was 25 grams. So now an extra mass was added. So we had the extra mass of we don't see no extra mass. So that's what we're trying to find. Then whatever information have been given. So the tangential speed that was reached was about 8.1 meters per second. Okay. So when you go back to our formula for centripetal force is given to be the product of the mass. Okay. Then v squared over the radius. All right. So that's the formula that we are supposed to use. Then we don't know the force, but in terms of we have this, what was happening there? What could have provided a centripetal force? Is it a tension, or maybe is it a friction? What do we think? Hello, how are we together? This is a very interesting question. Need contributions. Are we together, guys?
No.
Yes. Well, you have a question? Where do you need clarity? You can ask. Okay, so is the message? Are we all unable to see the screen? Hello? Are we able to see the screen?
Yes, you're able to see.
So this is our question. So I was asking about the type of centripetal force, but what was acting when somebody is like trying to make a head spin using the air strand. So what are we trying to do? What is providing the support to the masses that are connected to the strand of the air? So is it a tension? Is it friction? Is it gravity? What are we saying? Hello? Hello, are you able to get me? Hello? So have you understood how I've collected this data? So the mass, so we have a mass of 25 grams. Yeah, we have the extra mass what we don't know, right? So now we want to determine now the, want to get to determine the what is happening. So what are we going to do? So we need to, what do we need to look at? We need to determine the centripetal force. So a centripetal force in this case acting along the strand was the tension. So how do you calculate the tension? For tension is just a force that is acting along the rope. And of course, we know the tension can also be given just by T being, since it's a force, it will be equal to the product of the mass and what? The mass and the acceleration. All right. So that's what we have at hand. And in this case, we're supposed to equate the two formulas for us to find for us to determine the extra mass that we've not been given. Okay. So just rejoin so that we continue. We barely have about a minute before this meeting expires. So just rejoin using the same link.